points, lines, and planes. So lesson 1 was points, lines, and planes. Lesson 2, we talked about line segments. Lesson 3, we talked about angles. Here we are, lesson 4. Okay, we're back to points, lines, and planes, but we're talking about the theorems and postulates that surround those. Essentially, this is review for the previous 3 lessons. It's kind of tying some things together, but a lot of it is stuff that we've already talked about up to this point. Okay, can anybody tell me what a postulate is? That should have been somewhere in our list of definitions and vocab. What is a postulate? Sure, Google it. Tell me what a postulate is. Let me see. Fact. See, these are all kind of different things. Okay? So the things that we would look for here based upon this are fact or truth. Something as a basis for reasoning, discussion, or belief. All right? So a thing suggested or assumed as true as the basis for reasoning, discussion. Basically, it is something that is agreed to be true without requiring proof. Okay? So it doesn't require proof. It is accepted as fact. Okay? I'm not sure that this is necessarily a good postulate, but if I'm trying to think of like some outward thing that you would understand is that Americans drive on the right-hand side of the road. Is that widely accepted to be true? Do we need to go outside and prove it? No. Okay? So the postulates that we're going to look at in this lesson, all of which help define the properties of points, lines, and planes, are essential to proving and understanding many of the most important theorems, should probably say in geometry, or of geometry. So we'll go ahead and change that, of geometry. Okay? Through any 2 points, there exists exactly one line. Right? We talked about that day 1, but that is in this book what is referred to as postulate number 5. It is a fact. It is something that is assumed to be true without proof. Okay? Through any 2 points, no matter how far or how close they are to each other, there exists exactly one line. Doesn't matter how many points there are, through any 2 points there is a line. Okay? If you represent a point and I represent a point, between me and any student in this room, there exists exactly one line from me to you. Okay? If all students in this school represent points, there exists exactly one line, no matter what it has to cut through, that exists between you and another student. Okay? If you represent a point. Okay? So basically all of this is just theorems and postulates, things that we should already know. Theorem 4-1. Okay, if 2 lines intersect, then they intersect at exactly 1 point. Is that new information to us? No, that was lesson 1, right? Where do 2 lines intersect at? At exactly 1 point. Postulate 6. Through any 3 non-collinear points, there exists exactly 1 plane. So we could reverse the question and ask, how many non-collinear points do I need to identify 1 plane? 3. Okay? I need 3 points to be what in order to identify 1 plane? I need them to be, let's use the terminology, non-collinear. Okay? They cannot be in a straight line and identify a plane, if that's all I have. Okay? If 3 points are collinear, then there are an infinite number of points that can be drawn through them. Essentially what we're saying is that, all right, let's take this as a line, okay? And this paper is a plane, all right? I can twist that paper around it, and I could stop at any given point. It would represent an infinite number of planes, because remember, a plane has no thickness, okay? So if I just have a line, Okay, draw this thing out invisible and imagine a sheet of paper. I can twist that thing and stop at any given point, and as that line is still on it. Okay, theorem 4-2. If there's a line and a point not on the line, then exactly one plane contains them. All right, and you can, again, I think you can see theorem 4-2 is on page 22, and they have a picture there that you can look at. Okay, theorem 4-3. Here's the thing that I don't like about necessarily the labeling on some of these is that the only reason it's called 4-3 is because it's in lesson 4 and it's the third theorem. So theorem, if you end up running into something and, you know, hey, what is the proof for this? The proof is the definition. The proof is not the theorem number, okay? Because this theorem, if two lines intersect and there exists exactly one plane that contains them, that could be a completely different theorem number in a different textbook. Okay, so the definition is the proof. Okay, not theorem 4-3. So if we're going to end up doing proofs later, the statement or the reason that something is true is not theorem 4-3. The reason is if two lines intersect and there exists exactly one plane that contains them. Okay? So with postulate 6, 4-2, and 4-3, those give conditions for determining one plane. If any of the following would be sufficient. If we have three non-collinear points, if we have a line and a point not on the line, okay? The part about a line and a point not on the line forming a plane is because how many points do I have to have a line? So I just have to have two. So if I have 2 points, there's a line there, and I have a third point that's not on that line, what are these 3 points to each other? They're non-collinear, so between any, if I have a line and a point not on the line, there exists exactly one plane because what they are by definition is 3 non-collinear points. Does that make sense? Okay. Or 2 intersecting lines. 2 intersecting lines form a plane, even if those 2 lines also exist on different planes. Yes? I have to have 3 of them. They will, if I have 3 non-collinear points, they will form a triangle. That means there's a plane. Okay? They're not going to put that type of definition out. They're not going to say triangle equals plane in your book, but essentially, yes. Okay. Just as 2 lines intersect in exactly one point, 2 planes intersect in exactly one line. Postulate 7, if 2 planes intersect and their intersection is a line. We talked about that, right? Ceiling and the wall intersect at a line, a corner. Postulate 8, if 2 points lie on a plane, then the line containing the points is also on the plane. For instance, could we accept this cue card here to represent a plane? Okay, so if I draw 2 points, okay, we can agree that those 2 points are on this plane, right? Okay, what can connect those 2 points? A line. Where would that line be? And where would it exist on this plane? Yeah, because, okay, so some of these are going to seem like that's kind of dumb, obviously, yes, okay, but those 2 points exist on that plane, so the line that connects those points also exists on the plane, okay? And these may seem silly now, but later on we're going to look at questions and scenarios and geometric type things where we're going to need to know that, okay? Let's see, postulate number 9. A line contains at least 2 points. We know that. A plane contains at least 3 non-collinear points. We know that. Space contains at least 4 non-coplanar points. Okay? So 4 points that are not on the same plane is what it takes to define space. Otherwise, what we would say is that 3 non-coplanar planes are needed to define space, but that's going to take at least 4 points, non-coplanar points. All right, and that's it. So if we look at, and I don't have it pulled up here, let's look at a few questions. Let's see. I'm not quite sure. I probably have a schedule somewhere that tells us what time that we get out on an early out day. But I don't want to keep you guys too long. I want you guys to be able to work on your homework. There we go. If I can find the schedule, let's check. We get so much paperwork, it's hard to keep everything in order. There we go. Let's see. 8:45. What's that? So 5 minutes. I'll pull it up and let's answer one question. Okay. Let's see. Number 1. We might be able to get through some of these pretty quick. Identify all points of intersection of lines shown on this plane. Your points of intersection are going to be point P, point G, and point R, right? Those are points of intersection. Okay. Number 2. Identify the plane in the diagram that contains AC. So it's got to contain AC. So ACR doesn't work because R is on the same line, right? I need 3 non-coplanar points, or sorry, non-collinear points to identify a plane. Plane WCT. Plane WCT, it does intersect it, which would put it on the same plane, but it doesn't identify a plane because they're 3 collinear points. WRT, okay, WRT, okay, it intersects and they're non-collinear, okay, whereas RCA is also that same line. So we would want WRT to be 3 non-collinear points that identify a plane that ACR is, or that line AC is also on. Okay? All right, so with that, you guys got about 3 minutes. Try to get at least a couple of questions done or started on your homework, and if I can help you out, I sure will.